So we are putting everything we've talked about identifying characteristics of functions together now in order to sketch the graphs of rational functions. And I love talking about these different characteristics of rational functions because there's so many like interesting characteristics. There's things we're pulling from studying polynomial functions. And then this is very like, once you get into the transcendental functions, you're able to fall back on these different skills of identifying x-intercepts, end behavior, points of discontinuity, right, like domain restrictions, in order to figure out what those graphs look like, okay? So for rational functions, identifying the domain, so usually factoring the numerator and denominator if possible, locating any hole, so like identifying the types of discontinuity, removable and non-removable, right? So identifying any holes, if there's any holes. Identifying vertical asymptotes, if any asymptotes. Using end behavior model to help you with identifying the end behavior. If there is an end behavior asymptote, so like a horizontal asymptote, being like, okay, horizontal asymptote, y equals this number. If there's a slant asymptote, doing the polynomial long division or the synthetic division in order to come up with the equation of the slant asymptote. You can identify y-intercepts and x-intercepts, right, wherever the numerator would be equal to 0. And then you can also do the analysis. Remember how yesterday when we were trying to determine whether the function was approaching positive or negative infinity as it was approaching a vertical asymptote, you choose like the test values directly to the left and right to check the sign. Yeah. So we'll do that to help us figure out what's going on. So we're going to do 1 or 2 of these together before I release you to train some of these on your own. So for m of x, the first thing we probably want to do is factor the denominator. What's the denominator factor to? Okay. No common factors in the numerator and denominator, which tells us something about the graph right away. No holes. No holes. We can see that x just can't be equal to plus or minus 1. Like that's the domain. If you were having to state the domain in interval notation, we would just say negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. All of this is kind of side work. Like our goal right now is to sketch the graph of m of x, but I'm going to also kind of take you through things that could show up as questions on your quiz today. So like if I'm asking you about points of discontinuity, we can say that there are what type of discontinuity is occurring and where? And where is it occurring? They're vertical asymptotes at 1 and negative 1. Good. Yeah. So putting that together, we can say there's non-removable discontinuity at x equals to negative 1 and x equals to 1. Those correspond to vertical asymptotes. So we can already sketch those. Let's put those in here. What about x-intercept? Where's the numerator equal to 0? 0. So it's actually the x-intercept and the y-intercept in this case, right? When the origin is the x-intercept, it's also the y-intercept. Now the graph can't cross these vertical asymptotes. For a rational function, like we know that vertical asymptotes correspond to non-removable discontinuities. The graph is not going to cross. We do know that the graph is either going to be approaching positive infinity or negative infinity as x approaches -1 or 1. So we could think about doing test values. This is not something that you have to write out. If for you it's helpful to write out, you can. But you can think about plugging in values directly to the left and the right of each of the vertical asymptotes. So like for -1, what's a value that would be directly to the left of -1? Sure. Okay, so if we thought about plugging -1.01 into the function.
Wait, so would this be like as x is approaching -1 and then a minus symbol on the top, from the left?
Yeah, so this would be thinking, this is kind of our thought process for thinking about as x approaches -1 from the left, m of x is approaching, and we're just checking the sign. Like the numerator would be negative. The denominator, though, would be positive. A negative divided by a positive is a negative. So that means that m of x is approaching negative infinity as x approaches -1 from the left. So what that means is that the graph, I haven't determined like end behavior asymptotes or anything, but I do know that the graph is going to be trending down to negative infinity as it approaches -1 from the left. Okay, thinking about from the right, as x approaches 1 from the right, and this is something you could do in your head. If I explicitly asked you a question about this, you should be able to answer it. But as x approaches 1 from the right, oops, I didn't mean to. So what's a value that would be directly to the right of -1?
Wait, to the right of 1 or negative?
To the right of -1. How about -0.99? Where numerator would be negative, the denominator would also be negative. A negative divided by a negative will be a positive. Okay, so that tells me coming off of this x-intercept that the graph is going to be approaching positive infinity. Now, our x-intercept, our 0, hold the thought, has a multiplicity of 1, which means what? It's an odd multiplicity, but it means that the graph is going to cross at that x-intercept. I don't even need to do the analysis, and it's not going to cross the x-axis again, so I actually don't even need to test directly to the left of +1. You, of course, could, but you don't need to. Zach, what was your question?
Wait, you said like to the right of 1. Do you mean from the right of -1?
Didn't I say to the right of -1?
Oh, I thought you wrote 1.
Yeah.
I was just making sure you're paying attention.
Okay.
Good job. Caught that. Totally meant for that to happen. But does everyone follow how we know what the graph will be approaching as x approaches 1 from the left? Right? So as x approaches 1 from the left, m of x is approaching negative infinity. And then as x approaches 1 from the right, so what's a value directly to the right of positive 1? Yeah, so if we did like 1.01 over 1.01 squared minus 1, that's going to be a positive over a positive, which will be a positive. So I know that the graph is going to be approaching positive infinity as x approaches 1 from the right.
So do we just eyeball that line, the extra line?
Say that one more time, Teo.
For the like extra lines that are on the left and right of the asymptotes.
Well, we're not done. So now we're going to look at end behavior to see how we can fit all the puzzle pieces together, okay, and see. So if we are looking EBM, okay, EBM would be y equals to x over x squared, which simplifies to what? 1 over x. What does that mean in terms of end behavior?
It's gonna be like the thing. Yeah, what I said.
So we can think about that as x approaches positive or negative infinity, m of x, similar to 1 over x, will approach 0, meaning we can say a horizontal asymptote describes the end behavior at y equals to 0. Now we could also check where the graph would cross the horizontal asymptote. This one's kind of an easy one that we could just do like a mental check. Like if we set m of x equal to 0, what's the only solution? 0. And don't we already know that point? So we already know the one point where the graph crosses the horizontal asymptote. Meaning we can put that together. We know that in Q3, this branch of the graph is going to end up approaching y equals to 0 from below. And then in Q1, this branch will approach y equals to 0 from above. You could technically find additional points. I'm not requiring it. It's more like you're just putting all of that information together. We know the graph doesn't cross the horizontal asymptote anywhere else. Like maybe this hugs closer to the asymptotes here. I don't know. I would have to do test value. But I know as x gets infinitely large or infinitely small, the graph is going to be trending towards 0. Teo.
Can you explain again how you got the horizontal asymptote?
Yes. So if this is our function, our end behavior model, like if we're thinking as x is getting infinitely large, infinitely small, is going to be the ratio of x over x squared. Are we comfortable with that? That will simplify to 1 over x, which means m of x has the same end behavior as y equals to 1 over x. So if we did the analysis for 1 over x, first of all, that's a parent function we're familiar with. But if you were doing kind of the thinking about plugging values in, as x approaches positive or negative infinity, 1 over x is approaching 0. So it's when, as x approaches positive or negative infinity, the y values are approaching a number, then we say there's a horizontal asymptote at y equals to that number. Is that better?
So it's like because you know that there's a horizontal asymptote in the 1 over x parent function, you can say it's at y equals 0 for this.
Yeah, so in this case, 1 over x is the end behavior model, like it's our reference, right, for the end behavior of m of x. M of x will have similar end behavior as 1 over x. In this case, when it's the horizontal asymptote at y equals to 0, m of x. You could also just think about it without like an end behavior model approach here. You could think as x is getting infinitely larger, infinitely small, the denominator in this case is going to be growing like so much larger, like thinking about plugging in like a million, a billion. The denominator will be so much larger than the numerator that as those values are getting larger, the y values would be getting smaller and smaller and smaller. Nicole.
So if x is a 0 and it has a multiplicity of 1, how come we aren't crossing the point 0 in a linear way?
It is kind of.
Because right now it looks more like a cubic function, like with the little s things. I thought it would be just a straight line.
It would be more at, like if we were to, okay, let me think about how to explain this without, okay, so if I put this in here, woo, gotta zoom in, zoom, 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 zoom. Okay, how about this? If we were to zoom in on this point at 0, 0, what's the graph starting to look like? It's what we call locally linear at 0 versus if we were looking at like x cubed or something that did pass more of an S shape, it would flatten out to where there would be more of like, it would almost look more like a horizontal line if you were to zoom in really close. So that's the difference. So if we zoom in,
It does pass it as a straight line.
it's just there's some curvature to like between the vertical asymptotes, but it's not as S-shaped as, let me see if I were to put in.
Does the line have a specific slope?
Wait, so she has to be
Is that 45 degrees or like just like
hopefully.
There are ways to determine that slope. I don't know how far there are ways to determine the slope. I'll just say that. So if I put in x cubed here, look at that. That's x cubed. Did you see the black?
Oh, yeah, the black line.
Here, can I change the color? Am I able to do that? So see how that's almost horizontal, like it levels out versus passing straight through. So that's the difference with the multiplicities. Yeah.
But it kind of like the actual graph, like it kind of looks like a reciprocal parent function, like a y equal like y over x, because of those like lines. But that's like your behavior model. Does that have to do with anything? Or, like,
It's just that it has as x gets infinitely large. Remember, you can the way I think about it is the terms in the numerator and denominator as x is getting infinitely large or infinitely small as being at like a tug of war with each other. So like thinking about like as x is getting so big, which terms are really going to overpower the other terms. So because in the numerator we only have x, okay, x wins the tug of war in the numerator, x squared wins the tug of war in the denominator. So as x gets so large, it's really just the ratio of x over x squared that's going to impact the output values for y, which x over x squared simplifies to be 1 over x.
okay.
So it's a model for end behavior. It's not really like a parent function. But really good questions, you guys. We did pretty good. If we compare, I think it's always fun to like compare your sketches with Desmos or with your graphing calculator to see how you did. We did pretty good. let's do one more together. And I might have you guys try one. Okay, so first order of business, why don't we factor those puppies? Let's see what we're dealing with here. So in the numerator, I'm sorry, what in the numerator? 2x, that would be minus 3 minus 2, right? Because minus 4x minus 3x would be negative 7x. And then in the denominator, we would have minus 4 plus 1. Okay, so we already know something about the graph. No common factors to cancel, which means no holes. Now, that's not something you could put pencil to paper, but it is something that's telling about the graph. We know there's no holes in the graph, okay? And something that's telling about the domain, right? So x can't be equal to 4, negative 1, and both of those domain restrictions, so if we're stating the domain in interval notation, negative infinity to negative 1, union negative 1 to 4, union 4 to infinity. Both of those domain restrictions we would classify as what type of discontinuity?
Non-removable.
Non-removable, good. And that's because graphically, both of those points of discontinuity manifest as vertical asymptotes. Which we can sketch. Oops. A little bit off. Here we go. How about x-intercepts, you guys? Yeah, 3/2, comma 0, and then 2, comma 0. We can plot both of those. Oh, they're really close together, huh? And then we know that both of those zeros have a multiplicity of 1, so the graphs will just cross straight through at both of those. So my thought is there's going to be kind of a well, would it work? Yeah, there's going to be either a U-shape this way or a U-shape this way. And we'll have to do some extra thinking to figure that out. What's the y-intercept?
0, comma, negative 3 over 2.
Good. So actually, that's really helpful. That's an important puzzle piece, isn't it? Because the graph can't cross through the x-axis again. So what that tells me is that the graph is probably going to trend down towards negative infinity here, cross through a little bit there, and then trend down towards here, just because those are the only two x-intercepts. Now, you could do the test values to the left and right of the vertical asymptotes, like just to confirm that. But like that's the only way that we would have our y-intercept below the x-axis. We could think about test values to figure out what's happening to the left of x equals to negative 1. So like if we're thinking about as x approaches -1 from the left, what f of x is approaching, we could use like a negative 1.01 or something. And you can just think about plugging in to the factored version. So like that would be a negative times a negative would make a positive over a negative times a positive would be a negative. So that means f of x would approach, go away Siri, would approach -infinity. Do we follow that? I was thinking about plugging in here, negative 1.01.
Wait, how do you?
Oh, wait. Did I screw that up?
Use positive.
It would be positive. You're right. No, you're right. It would be negative times a negative.
Wait, how do we know that it's a parabola and not parabola, but it's going down, but not like...
So you have two options. You could do what we're doing right now with the test values, and you would see that, like, if you were plugging in, let's say, negative 0.999, okay, you would end up with a negative ratio. So that would indicate negative infinity. But the way that I thought about it is if these are the two x-intercepts, these x-intercepts, both of those zeros that correspond to the x-intercepts have multiplicities of 1, so it crosses straight through. So I knew that for the graph to only cross through those two x-intercepts there, and with these vertical asymptotes, the graph's either going to have to be kind of the U shape pointing down or pointing up. Because you pointed out that the y-intercept is at 0, -3/2. That means that the graph is going to have to be trending downwards, right? Because think about it. If we have passing through the y-intercept, okay, has to pass straight through 3/2, 0, and then come down through 2, 0, and then not pass through the x-axis again, it just has to trend downwards. Again, if you didn't recognize that, there's nothing wrong with thinking about doing test values. So as x approaches -1 from the left, f of x is approaching positive infinity. And then I also still need, as x approaches 4 from the right, so like 4.01, that would be a positive times a positive is a positive. And then a positive times a positive, right? Would be a positive, so positive infinity as well. And then the last piece of the puzzle is end behavior. So our EBM is 2x squared over x squared. What's that simplify to, you guys?
2.
So that means that our end behavior is the same as a horizontal line, y equals to 2, right? So as x approaches positive or negative infinity, f of x is approaching 2, which means there's the horizontal asymptote at y equals to 2.
Wait, can you like not do the EBM and just calculate the horizontal
Yep.
asymptote in the
EBM is side work. So if you're somebody that's like memorized the exponent rules or something, or you're doing just a numerical analysis, like thinking as x approaches positive or negative infinity without thinking of identifying EBM, that's fine. And then the last thing that I want to do before finishing my graph off, putting all those puzzle pieces together, I want to figure out does this function cross the horizontal asymptote anywhere? So in order to do that, I'm going to think about setting f of x equal to 2. I'm going to do that over here just because I don't really have space. So let's see. So if we set f of x equal to 2, right? Because this is how you would identify a point of intersection. You're seeing, are there any x values where the y value for a rational function would be equal to 2, and therefore cross the line y equals to 2. So we can multiply by x squared minus 3x minus 4 on each side. I'm going to pause for a second. Is everybody comfortable going here to here? I distributed the 2. Okay, 2x squareds will cancel. If I add 7x, I'll get x. If I add 8, I'll get 14. So at the point 14, comma 2, the graph will cross y equals to 2. That's kind of going off of the graph, so we could think about it like if this, put this up here. If this were extending ten, 11, 12, 13, 14. So the graph is going to come down and it'll cross, but it's still going to stay close to our horizontal asymptote. Like it's not going totally crazy. And then it doesn't cross at all on this side. So they're not symmetric.
If it approaches the horizontal asymptote at infinity, could it cross it again at another point?
No, because we've just solved for the only, there could be multiple points. This one, there's only one solution to that equation when we set f of x equal to 2. So there's only that one point. Here.
On the quiz or test, would we have to like extend the graph to show that it crosses if we know that it's going to cross? Or can we just like draw the line and leave it like that? If the graph is too small.
No, you could just show like what the x and y axis that I give you, like that region. Unless I like explicitly ask you, does this cross the horizontal? Like you should check and see, does it cross anywhere? But if that's off the graph, it's fine. All right, you guys, I would like to give you, or let's check how we did. Let's check how we did. And then I'm going to give you guys a break.
I have a question.
I might have an answer. What's up?
If we have like a hole and then since we like cross them out, if we have like a test point for anything that I have to put back into the equation, do we use the second, like where we cross it out, or do we use the original equation?
The graph it doesn't matter, right? Because the graph is going to look like the simplified version of the equation. So you want to take into account that hole. We haven't had one. We will have one where there will be a hole, and we'll want to sketch that. But it doesn't matter because all of the other values in the domain and range are going to match up with the simplified version. Boom. And then if we were to put in y equals to 2, see? Boom. Crosses 14, 2. All We did good. All right, you guys, let's take like a 10-minute break. That was a lot.